Good? Might as well tell you this. I posted something on OneNote. How many saw it? Here's the upshot. This course has to be assessed by ABET standards. That's an accreditation board. And I was told by Dr. Reeves, this is the first time for me to have to do this kind of stuff, is that it requires, this is going to be in place of your MATLAB project, but it could be your MATLAB project. It requires you to come up with a problem, in my words, harder than the homeworks, something more difficult, that require you to formulate. Just listen to me. I didn't like it either. It sounds like somebody's been out to California too long and came up with some wild thing. Anyway, they want you to formulate a way to actually solve it, then go ahead and execute the formulation, do a brief write-up, and display the results in a professional format. Now, I posted the information. So I gave you an example. That's actually Wentworth's example. So, for instance, if Matt, is it? What's your first? And what's your name?
Tyler.
All right. If Matt and Tyler come up with two things, and I'm going to give you ones. He's always doing the Wi-Fi. I mean, he's got the recording. He wants to find out the electromagnetic interference path between this microphone and whatever, that receiver interference. So he comes up with some theoretical interference in the spectral domain, and then he finds a way to reduce it. All right, now this is wide open. All right, but you've got to formulate it. Give me sort of the nitty-gritty, the path that the actual signal's going on, the interfere, how you're going to mitigate it, measurements before mitigation, after mitigation. It's all theoretical, so you don't even need measurements. Do it on MATLAB, find out what's out there in the journals, find out somebody else that did something similar, and try to develop something on your own that's novel. Now, here's the thing you got to be aware of. These guys have all sorts of software. The people who look at this have software that can see if you plagiarized anything. So if for somewhere out there, you try to rip something right off the internet or off an IEEE and just do exactly, like word for word almost, or you're doing exactly what they've done, they're probably going to call a flag on. Right? And you're probably going to get, in some way, shape, or form, in trouble. And probably get me in trouble because I didn't catch it. But I'm just telling you, try to just do this, your best job, do it on your own. Now, you're going to have to hand this in if you want to graduate. You're not going to get a grade in this course unless I have that. So there's nobody gets a pass. Everybody has to do it. How many looked at the example I gave you? Right? That was a bizarre one. You want a bunch of turns of wire, assume the magnetic field is constant. This is Emag2, not Emag1. And assume the magnetic field's constant in there, figure out the magnetic field, what it is, then estimate the inductance, I think was what it came down to, something like that. That's a very easy problem. I would expect something a little more complicated, but not really complicated. If you want me to suggest some things, I will, and I'll tell you great places to look. Right now, we're doing EMC, right? Boy, there are EMC problems galore. I'm trying to think of one that you run into. Back in the day, the hairdryer was the EMC problem. If you turned it on, it had a TV or something like this, you'd hear that but this is standard. This is FM. It's encrypted. Is this encrypted or non-encrypted, the signaling? EMC is a rich area. You can find EMC problems in your car, probably. Actually, nowadays it's pretty mitigated now that I think about it in the car. But there's all sorts of problems where you get interference on your cell phones. If you've down here, we don't even get cell phone coverage, I don't think, unless you got Wi-Fi. If you're using voice over IP down here, when you click it, then you can actually communicate. But I have T-Mobile, and I can't talk in this downstairs basement. Verizon, I think, can. The only way I can talk is if I put on the Wi-Fi calling, and then I can. But can you all see what I'm trying to get you to do? Now, you can do stuff with antennas. Come up with a problem with antennas. Here's a good one. And this is one I like because it gets me something free. All right, now Auburn has a Wi-Fi signal right here. Are you with me? So if you have an Auburn ID and you're a student, you can get on the internet right here, right? Wouldn't it be nice to do that at home? Answer, yes. Sure. Where's home? Well, go about a mile or two away, line of sight. You can't get it unless you had what? A very high gain antenna. And then you could transmit from your house to here, back and forth, and you could do it. Well, what kind of an antenna would you need? Come up, go measure the signal out there. You can do this with your phone, or you can actually estimate the signal strength very easily for cell phone towers. Find out the nearest one, and you can get what's called the estimate of the signal. There, it would be the minimal signal. It's the antenna. The cell phone towers have what are called an antenna footprint. Are you familiar with this? In other words, their antennas just don't broadcast horizontally everywhere. It's a footprint usually that they're aiming most of their energy at, but they get spillover. There's plenty of spillover on these things. So you could estimate what signal strength's out there, what antenna you would need to do it, and then come up with a little MATLAB simulation of a supposed signal coming there and back and find out like the round trip time. Are you with me on this, class? So before you do it, I want you to come to me and explain what you're going to do and let me give you the green light. But you have to come up with something. And this isn't hard. I'm not expecting, 50 hours of work here. A little creativity. Come up with a reasonable problem. Make it up yourself. I can give you some more hints. And then come to me with it and then go ahead and solve it. I'd like to see some MATLAB in on this one, all right? Just because there's a lot more pressure right now to make the kids use MATLAB formally in the class, and I'm pretty lenient about that, except for the senior design. So this is going to take the place of the senior design. Are you all with me? Now, there's a lot of people in here. There's probably room for a whole bunch of unique projects. If you talk to some of the kids that had 3320 before, you can see what they've done. I don't know what they've done. I haven't talked to them. But Wentworth taught that in the spring, and they did that in the spring. I think Wentworth did. Did he? I think he taught it in spring, but I got to be careful. Somebody taught 3320 and assessed it, and they did this very thing. And I'll admit, I don't like it. Because in the real world, you're given a problem, then you come up with a formulated solution, then you do it and give the results back to the boss. You don't say, what can we do? Well, this looks like a fun problem. And it's got to be related to this course, all right? So it can't be shooting a rifle at something 100 yards away. It has to be related to this course. Yes?
So you said this is taking over the MATLAB project? So here it's like, it says 20 points of extra credit.
Up to 20, it's going to take over. What I'm going to do is this. You can get up to 20 points. Now, listen to me. This is a gift. If you do it right, do a good job, those 20 points get shoved into your quiz average, right? If you miss the quiz, there's one quiz that gets trashed, right? So now the remaining quizzes plus this up to 20 points gets added on. It's still the same number of quizzes minus one averaged in. So that really could boost your score if you've blown a dozen or so. I'm trying to be fair about this, guys. I mean, I've got some pressure on me, and I don't really like it because the way I do things is I give you a project, you come up with a solution, I make it unique in a sort of a sneaky way because I use your name to come up to translate that name into letters and digits, and that tells me or tells you the actual orientation of the antennas and the number of elements for an array, and then you have to go ahead and get. That's what I did in the past, and it was all sorts of whining, but kids did get it after a while. So, any other questions? Anybody got any other ideas while we're here? Yeah. Perfect. That's ideal. You even got a real thing. I mean, it's a real problem. Yeah, perfect. Find a way to get rid of it and do it. Write it up, formulate the plan, and I can help you with some of that. Here's a tip. Ferrite beads and common mode choke. Both of those things can help. I'll talk about ferrite beads later. Go ahead. Anything else?
Mic fell off.
Huh?
Mic fell off.
What?
Mic fell off.
Oh, did it? Rotten Mike. Anything else?
What's this to?
The MATLAB project used to make up 10% of our final.
It's going to be, I'm going to alter this stuff to adjust everything. I'll get that adjusted scale. Look, I found out about this a few days ago. But I'll get that to you. All right, so. Yeah.
When's it due?
Well, I want them in the last week of class, all right, the last week. But if I was you, I would get a leg up and just get it done. It's not hard to do this. Just make sure you do it. And the one thing I'm going to tell you, one last thing about this, is I don't know what's out there, but I'm told that they have software out there that will literally identify plagiarism now. very well. They have, it's AI basically. And if they find something out there that you basically just ripped off the internet or ripped out of a journal, they can nail you. I don't know at what level they're at, but I'm hearing that. And when I hear this from people that up at Samford and other, and John Hung is involved heavily with the journals. Now they're catching people, literally people that are professors and stuff, that are really just, they're plagiarizing other people. Now here's the way it really goes on. This happened to a guy and he got caught, got in a lot of trouble. Guy needed to get his doctorate done, so he was Italian. He looked in Italian journals, found an entire doctorate in Italian that had not been translated to English years ago. Basically took that, translated to English, and it became his doctorate. And he was at a national lab. And it worked for 5, 10 years, something like this. Then all of a sudden, the software came out that checks that kind of stuff. And he got nailed for it. Now, I don't know what happened to him, but that's kind of the worst thing possible. That was a doctorate. That wasn't a class paper or something like that. So just remember that they've been developing this kind of software for a while. And I guess the English department uses this too, from what I've been told. I don't know what it is. I don't know how they do it. But they go through all the journals. And whenever there's commonality above a certain level of correlation, all of a sudden it pulls that paper out and starts comparing it at a higher level. And then if there's like a 90% confidence interval, it's a plagiarism, then boy, I don't know. I wouldn't want to be that guy or that girl. Yeah.
How many pages do you want on the board?
I'd say probably 2 with figures, and I'm just going to say what I'd like to see is the mathematics more than I would a lot of words. I don't need. I get this sometimes on literally tests with problems like circuits and stuff. People are writing me an essay. I don't grade essays. I ask for the current and the voltage. That's all I care about. All right, so just make it clear. The idea is when you formulate the problem, clearly define the steps you're going to take to solve the problem or to design something. You know, it's most of this, it's so open, it's more of a design than an actual hardcore analysis. Any other question? I'm trying to talk it up with you because Dr. Reeves suggested I spent a little time motivating you. I don't know how to motivate you. Yeah.
This is kind of unrelated, but are we voting for the test?
We will be in a second. I hope everybody showed up. It looks a little thin to me, but that's just me. I don't know. Maybe people aren't going to show up. We'll vote, and I appreciate that. Yeah.
Can we do, I don't know if this is a book, but can we do like 110 volts versus like audio and how that interference is the cable and.
Do you mean the 60 hertz, 110 volt signal bleeding in? Yeah, that's conducted emissions. Look up conducted emissions, and if you want to do that, that's fine. Is that what you're going to do? Good. One thing done. But there's a lot out there. Just think of something clever related to either EMC, antennas, shielding, propagation through, you want to do something crazy? There's a lot of talk now about actually when buildings collapse from earthquakes, having the emergency management people being able to communicate through the walls to stuff, because when people's cell phones, you know, when these buildings and stuff collapse, because they have that reinforced gridding, steel girders, they aren't able to talk. And it's almost like being in a tunnel. You ever gone through a tunnel and see your radio knock out and everything like that? Well, it's the same thing when a building collapses. All right, you may be alive under there, but nobody's ever going to know it. And it happens all the time, believe it or not. And so they're looking for some way to mitigate that. The whole idea, the way you do that is called wideband signals at very high frequencies. And you can have an emergency band that's going to be at a much, much higher frequency, and it'll have a wide bandwidth, and they can actually communicate very well through walls. The police have some of this stuff. When they have the, what do you call those, SWAT teams that go in and stuff like this, they have special communication packages that aren't generally available. All right, anything else about, anybody got any other ideas? You got an idea?
Yeah.
What?
I want to do a simulation of the interference patterns generated by arrays of antennas.
You mean the antenna pattern?
Yeah.
Well, that's kind of a done deal, but can you find something unique, a twist?
The example you gave is a done deal too. It's been done before.
Yeah, by my students, I know. I gave it to them. You talking about the one I'm giving you? I'm not talking about the mutual. You're talking about actually including the mutual impedance of the elements as well as their own. The one I gave was, it assumes you can drive antennas at a given current with a given length, all right, at a given orientation. And then you have X of these things. So you get the antenna pattern. That's not an easy thing to do, by the way. The thing is, a real antenna, there's mutual impedance between all the elements. So the actual current developed here has to do not just with the antenna here, but with all the other antennas' interactions. So that's a much harder problem. If you want to do that, then use NEC. Look, NEC. It's a code, NEC wire code for antenna simulation. You'll see it. Anybody else? I'm just trying to get, I've got one, now I got two. That's yours. Huh?
I didn't say I was doing that for sure.
I did. Now you're doing it for sure. Sorry, you can't drop an idea now. Now you've defined it. Anybody else? I'm just playing with you. I'm not kidding. If you want to change, don't worry. Yeah.
Could I calculate the size of an antenna needed to meet a certain length budget for a satellite?
Yeah, that'd be great. That'd be great. Super. As a matter of fact, yeah. And make sure you show satellite position, not just the vertical distance, but the actual off-axis distance. Talk to Riggs about some of that. Yeah.
Someone else would like, but shielding, like different shields, like their development, and like maybe.
But you're doing the thing already, right?
I don't know, I was just telling you for someone else.
Shields, you can do all sorts of things with shields. You can have minimal thickness shields. You can have shields minimal weight. But you have to almost define the problem you're trying to use the shield to eliminate or mitigate. You're an electrician. How about lightning remediation? That sounds like something up your alley. Figure a way to get the grounding run. Just think about that. That'd be probably a good pro. There's a lot out there. All right, well, do me a favor. Don't put this off till the last minute. I'll ping you again on this. Now, about the test, which he brought up, and I'm glad he did. We have Thanksgiving coming up in a couple weeks. I don't care if you want it before or after Thanksgiving. It's up to you. Does anybody have a preferred date for the test? Give me both day of the week and the actual date.
Next Wednesday, so.
Next Wednesday? Let's get this up on the board so at least we have a starting point. So Wednesday, right? And that would be the 13th, is that right? All right, well, look, it's just the beginning. Another date? 18th?
Stop doing that.
20? Anybody else? Any other dates? We're going to be, the following week's Thanksgiving. All right, so. 22nd. All right, now here's the deal. All right, here's the deal. Y'all are going to vote. And the top, if we have a lot of stuff in 3 boxes, the top 2 remain, and then you vote again. But we're going to do it quick. Can you count with me? All right, I just want to do this. So just for the record, if anybody wants Wednesday the 13th, one hand. One hand indeed. All right, you don't vote anymore. All right, now, do you want to vote on this Friday or not? All right, you want to vote on Monday? Well, just wait a second. There's hands going up. If you want it Monday, one hand. Now, count with me, all right? Count with me. I'm counting 1, 2, 3, 4, 5, 6. Wait a second. Let me do it again. Hands up and hold them high. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got 10. Is that right? 10. All right, now you guys can't vote again. All right, if you want it Wednesday the 20th, one hand. Now hold it up, just one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Is yours up? No, 18. Did you get 18? Some. All right. And if you want it Friday, well, we're out of people, but don't vote again. Friday the 18th, one hand? Anybody? Okay. It looks like even if we put this guy over here, that wins. And we're really short on people today. All right. Wednesday the 20th, the test. Got me? And can you send me an email reminding me the test is Wednesday the 20th? Just, and make sure you put it in the subject line, 3320 test. All right, thank you. Now, yeah, Allie. Hold on. Shh. What? What, you mean the page or what? We did really. Remember, every test is comprehensive, so it includes all the past material because you can't do the future things unless you know about wave propagation. You can't do antennas unless you understand that. You can't do a lot of stuff. So really, if you look at your last tests, right? We did really wave propagation, skin depth, right? But you didn't have radar, you didn't have antennas, right? So that's what. Say again. Yeah, I'm sorry. We didn't do freeze transmission, radar. I'm thinking about both ways. You're right. I did give you the equation. You're absolutely right about that. But it would be that EMC, filters, that jargon. All right. Now, I gave you some homework, and I'm going to cut to the chase with this stuff. Most of the problems that you'll see are like this, and where you have both the mutual impedance. You basically have common mode chokes, right? So then you have the different way it looks differentially, the way it looks in common. I want to do these problems with you real quick before I move into the next chapter. All right. So for the first problem, help me out on this one. What we did is we had a common mode choke like this, right? And here, and they had a mutual, and then they had a self. And they had, I think this is small a, and this is large a. Correct me if I'm wrong. And this is that right?
That's right.
Small b and large b here. And what they do is say this, that when they calculate the impedance, I'll call it Z small a b, when they hook it like this, they take this wire and run it here, or actually, and then they measure this impedance. It's actually small a capital B. They measure an impedance here. Can you give me what that is? Because I frankly don't remember.
The impedance at 50 megahertz seen looking at terminals A, B is 10 to the 6th at an angle of 90 degrees.
50 megahertz. So it's 10 to the 6th at an angle of?
90 degrees.
All right, that's just J. And then that's this connection, right?
That was small a to capital B.
Yeah, that's it. This is capital B right here. That's right. And then they have Z, and then it's small a, small b, right? Right? That's the other one. What's the other impedance?
They have capital A, capital B connected. That one is
What is it?
capital A, capital B,
300,000?
300,000 at an angle of 90 degrees ohms at 50 megahertz.
And these are ohms. All right. What I did was I put the labeling. The small a is at the other side, capital A. I think they got the capitals here, don't they?
They have the capitals on the right side, the lowercase on the left side.
Small AB is 300,000.
This is small b, that's small a? All right, well, if they hook it like this, let me explain something. Let me do it this way. This will be clearer to see. If I just take this connection and put it here, and then I measure this impedance. Follow me what I'm doing? Now, I want you to look at this, because here's what you have to decipher is what they're actually talking about, if it's common mode or if it's differential. Current's flowing through here into the dotted terminal. Does everybody see that? Just assume you got a current there. It goes into the dot of the first terminal. The first winding. Do you all see this, class? Comes there, comes down this way, and then it moves into the dot of the second terminal. It's going into the dot. Do you all see that? Into the dot here, into the dot here. Do you all see that, class? That means it would be common mode. When currents are going into the dotted terminal, same value, same current, common mode, right? Now, if they're common mode, it means the impedance of those things look like this. you're going to have the first winding here, and this will be equal to J omega, and it will be L plus M, the mutual plus the self. Do y'all remember when we did this, right? And then when it comes down here, here's the second winding with a dot, and this is going to have J omega M plus, or L plus M as well. And the goal is to find out what L and M are. Do you all follow me on this, class? How many see this and understand? That's common mode. With common mode, the impedance of each coil is really going to be this, the J omega times both the self, the L of that coil, plus the M, the mutual. That's what happens in common mode. Now, we know the frequency, and therefore we write this equation. We can say this right here, J omega, and omega is 2 pi times 50 times 10 to the 6th, J omega times the quantity L plus M, right? 1 time, 2 times, so you put a 2 out in front of this. That's going to be equal to that impedance right there, which is the common mode impedance, which is 10 to the 6th, right? And instead of putting 90 degrees, just put J there. Do you all agree with me, class? Can everybody understand what I've done here? There's 2 coils. Both of them have an impedance of J omega L plus M. That's the equation. Agreed? Everybody see this? Or not? If you looked at the homework, you realize that there's either common or differential modes. The only choices you have. This is the common mode impedance. The way you know it is, if you're measuring the impedance, just assume a current goes in from the small terminal A. The only way it can go, if it goes in the dot of the top, it has to go in the dot of the bottom, the way I've connected it. You got that? Everybody with me on this? So that means you know that L plus M, by the way, here's the nice thing. You can get rid of the 10 to the 6th right there. And now I can say, and get rid of the J. And now I can say that L plus M here will be equal to simply 1 over 4 pi times 50. That was just 10 to the 6th, correct? Isn't that right? And it's 50 megahertz is the frequency, right? All right, so now I know that. Is everybody all right with that? Now what else do I know is this, that when I hook these things this way, this is going to be the differential way, just watch. Now when I take the first coil, and this is small a, here's the second coil, there's small b, there's a dot here, dot here. Now common mode currents would flow same current into this dot to this dot. That'd be common mode. For differential, whatever flows there, the exact same magnitude, opposite direction would be flowing there. Do you all see that? This is differential. Now for differential, we have a current here, and it comes out here. So it's a differential mode. For differential mode, the impedance of this winding is J omega, and it's L minus M. And this winding is J omega L minus M. Are you with me? Please be sure you got this. So therefore, the total impedance between A and B for differential, this is the first thing we solve for, would be equal to, now we're going to have 2 times J times 2 pi times 50 times 10 to the 6th, right? That's going to be equal to, or times L minus M, so it's 2 times J omega L minus M is equal to, and now it's 300,000 at an angle of 90, or it's really just J, and then you can say 0.3 times 10 to the 6th, because that is 300,000. Do you agree with me? The reason I want the 10 to the 6th is so I can cancel them. Are you with me, class? 300,000 is 0.3 times 10 to the 6th. Agree? Can you see it, Duncan? You're looking around his head. Are you with me? Now, if you can see this and you understand it, then you can see the 10 to the 6th cancel. That's the only reason I did it this way. And now I can see that what? The J's cancel too, right there. And I can see that L minus M is equal to 0.3 over, and this is going to be 4 pi times 50. Agreed with me? Now, you do it any way you want. You agree if I add this to this, L and L is 2L. M minus M is 0. Agreed? So we'd get 2L here would be equal to, and now we add these up. And so I'd have equal to, you'll notice I have 4 pi 50 right there. So I have 1 over 4 pi times 50, 1 plus 0.3. Or if I take that and divide by 2, I get L. Can somebody just tell me what this comes out to? The answers are right for this one. Y'all?
1.035 millihenries.
Did you do the math? I mean, you ran it, this one?
No, it's the answer.
Somebody just do the math to me. I like to be absolutely confident. I'm going to tell you the reason I say this. Because I've gone through books that I really trust the answers in, and every once in a while, either with an edition that's printed or something like that, they're wrong. Not often, but sometimes. Just run the numbers and tell me what you get.
1.03 millihenries.
Okay. 1.03 millihenries. Now, for M, do it any way you want. If you've got this, do you realize if you want M, if you want that way, you're just going to take L right here that we just calculated and subtract it from that, and you'll get M, won't you, class? So what do you get? Isn't it 0.3 over 4 pi times 50 if you do that? Just tell me what you get for that. If you go ahead and you take, since we have L here as 1.03 millihenries, subtract it from 1 over 4 pi times 10 to the 50, and what you're going to see you're going to get is going to be 0.3 over 4 pi times 10 to the 50. Anybody give me that one? Is that what the book's answer is? 0.557 millihenries. Now, I'm going to tell you right now, that's an extreme difference. Most of the time with a common mode choke, most of the time, L and M are within 3 or 4% of each other or less. Most of the time. And that's the reasons they're so good, because if you look at this, if they're within 3 or 4%, then L minus M is about 0. All right? So the impedance for the differential mode is just about insignificant. The only thing it stops is common mode currents, and that's exactly what you want. Because when lightning hits, it tries to get through there, or if there's other ways for common mode to develop, then you never want common mode. It's the worst possible scenario for anything. Has anybody had to deal with common mode professionally or in the laboratory before, common mode troubles?
I use it on DC servos.
Yeah?
The DC servo.
You can get in trouble with that. My experience with common mode mainly came from lightning problems. All right, there are ground loops that can do it too that we'll talk about, but lightning usually did it. Which brings me to the last thing I'm going to talk about before we move out of here. This is just a little something to be aware of. This is going to be ground loops. Dr. Wentworth mentions grounds, but not ground loops. These are problems. Now here's why. First of all, what is a ground loop, all right? When you have wire and you're running it around anywhere, you create basically a loop, all right? So when you do that, if the loop's large enough, and there's a large enough time-varying magnetic field in the area, it'll induce a voltage. This should make sense to you, all right? It's called, it's basic EMF. It's the electromagnetic force that's from a time-varying magnetic field that drives the actual current around there. It's the basis for a generator. So why is a ground loop so bad? And let me just show you a typical thing. And I had this happen to me with a railgun, and I'll never forget this. Railguns cause a huge magnetic field. So we had basically something like this. Take this wire, and I'm going to make a simple loop like this. And really what you're having here is this wire represents some wiring that went around to measurements, all right, to a measuring device that came here, but it's a single wire. All right? It won't matter if there's 2 or 3 strands there. It doesn't matter. As long as there's a difference here, a point difference. So I want to find out the VEMF here. I'll tell you another thing. I think I told you about what you can do outdoors with one of these things with lightning, didn't I? The loop around the apartment complex in Huntsville. I didn't? I don't remember if I did. I did. Oh, it was in summer? All right, well, let me just tell you, here's another thing you'd never do. Make sure I catch me. We never want to do this. If you would take shellacked wire, the thin copper shellacked wire, and you would walk around a quarter-mile turn, say at Redstone apartment complex, just one turn around there, and then have the two ends be about a half an inch to an inch apart. Well, when lightning hits, it creates a large magnetic field. And some of that magnetic field is penetrating the closed loop. And the time-varying magnetic field times the area of that loop is the induced EMF, which is about 10 to 15,000 volts at times. So you get this beautiful arc across there whenever lightning strikes. However, it's something you never do. And you know, there's a lawsuit in here somewhere. I just know somebody's gonna, hey, just hold this, just watch. The kid dies. All right, so that's the EMF right there, right? Now, let's go through and just do a gag here. We're going to talk about what might happen with lightning with a single ground loop that's not even that large. So first I need lightning. So this is my lightning. I'm going to have I here, and it's going to be simply I'll make it I naught here, and this is going to be I naught is going to be equal to, say, 50 times 10 to the third. That's not much. It's going to have two time constants. It's going to have a e to the minus t over tau fall minus e to the minus t over tau rise. The fall time on this one is going to be about 10 to the minus 4 seconds, and the rise time is about 10 to the minus 6. So you got two time constants. The first one is the fall time, and the second is the rise time. At t equals 0, it's nothing, and it flies up at the rate of rise time to a peak, and then it turns over. Eventually, as t goes to infinity, this is 0. It's called a double exponential, and it looks like this. If this is t, it basically does this. And the peak is just shy of I naught. It's like 0.98 I naught. And that point is roughly about 2 times tau rise, roughly. Don't quote me exactly, but you can graph it and see for yourself. All right, so that's the current, and you can assume this thing's about infinite, okay? Yeah? It's t over tau rise. Tau rise is 10 to the minus 6. Tau fall is 10 to the fourth. So that's 10 to the fourth. That's 10 to the, or 10 to the minus fourth. That's 10 to the minus 6. Okay? It's standard, trust me. Now, if I have that, then the B field at a distance rho, we're going to let rho be about 1,000 meters. Right? If I come over and say I'm at a distance rho equal 1,000 meters, then I have a B field would be equal to mu 0 times I of t, that I of t, divided by 2 pi rho. And it would be in the A phi direction, but that's immaterial. It really is perpendicular to this loop. If it's going down, it's actually going in here. The B field would be in there. Do you all agree with me there? Very simple, right? I haven't done anything tricky. Now, just to give you a first order look at what happens. Now, if I have that as the B field, and this is my I of t right there, then what I can say is the total flux penetrating that loop as a function of time would be approximately equal to the area. And I'm going to say we're far enough away, so so the B field here is about the B field here. It's not quite true, but close enough. You with me? Roughly the same. Is the area, whatever that is, times the B field as a function of t. And that's the magnetic flux in Weber's penetrating the loop. Do you all agree with me? Now you can use, if you don't like the pitchfork symbol, you can use any symbol you want. The actual flux coupling is that symbol in Dr. Wentworth's book, but it doesn't matter. It's total flux. It's the integral of B dot ds over that loop. But since the loop, the B field's about constant, I'm just multiplying it by the area. Okay? Now, the EMF of t, which is really the voltage of t, is minus the time rate of change of the magnetic flux with respect to time. Agreed? All right. Now, what's that going to be? Well, it's technically minus a. That's just some constant that weighs the scale. And it's times the derivative of that. Now, here's the deal. When I take a derivative of this, you're going to watch this. This has a fall time that's much, much greater than this. When we take a derivative, we take 1 over the coefficient here out in front. Do you all see that? When I take a derivative, I can say this is about equal to, a derivative of that with respect to t is about equal to just I naught over tau rise. The minus sign cancels that. And it would be times e to the minus t over tau rise. Now that's an approximation. I ignored the fall time right here. I don't care about that. I only care about the rise time. That's what gives me the jolt. Now when you take a look at this at t equals 0 is about 0. I mean, but about 1. It's e to the 0 is 1. Do you agree with me? So it means this is approximately right here what the volt or what the actual voltage will be. Now I want you to watch this. I forgot mu naught. I've got to take the B field time. Sorry. I forgot the scale factor in here. It's going to be A right there. Then I'm going to take I naught over tau rise there. And then it's going to be times mu 0 over 2 pi. And then it's times rho right there. Now, I'm going to go ahead and just tell you how this works. A right here this is about let's see, 1,000, no, I'm sorry, 100 meters by 100 meters, so it's 10 to the 4th. I naught is going to be 5 times 10 to the 4th. It's 50,000. Mu naught is 4 pi times 10 to the minus 7th. Tau rise is 10 to the minus 6 times 2 pi times rho. I'm going to put it 1,000 meters away. Now I want you to just watch this. I'm trying to put you dimensionally into the ballpark. Watch the voltage on this one. All right, that's 4 pi times 10 to the minus 7th. That's the coefficient out there divided by 2 pi rho. Rho is 1,000. There's 2 pi rho. 10 to the minus 6 is going to be t rise. And what do you see going to happen here? Let me try to do this for you so you can see it. Right here, I got the 2 pi, 4 pi goes away. I got a 2 there, right? Then I got 1,000 right here and 10 to the 4th. That leaves me 10 upstairs, just 10, right there. I got 10 times 10 to the minus 7th. That's 10 to the minus 6. 10 to the minus 6 goes away. It's about 50. It's about 50. So what happens is this is about really 10 to the 5th volts peak. All right? That's 100,000 volts. And that's a fairly gross underestimate of what's possible for EMF with a ground loop. That's a ground loop caused by light, where lightning could get it. Now, the reason I used the dimensions I did is because that's actually one length of wire. It's actually short. There's less, this is less area than the actual area. If you walk around a quarter-mile track and lay wire like that, you're going to find out the total amount of area is, I say this, that's the outer part of the track, not the inner part, is going to be about this. It's actually a little larger. So even if I'm off by an order of magnitude, that's still 10,000 volts, all right, that comes across the end. That's one loop. You really want to have fun? And don't do this. Go ahead and spin about 30 of them. That's a lot of copper. And then watch the sparks fly, as they say. Now, I don't recommend you do some of these things, but what it's cool to do is search on YouTube, see if these things if there's anything out there, and just see what they get. Because when it's absolutely dark, and whenever lightning hits, you see a large arcing. That's pretty cool. Another thing I didn't tell you, I told my Emag in the summer this. Have you ever heard of? You know who Ben Franklin is? He's credited as being really the father of modern lightning research. And he had to know when lightning was going to happen. So there was a thing he developed called Franklin bells. And what he did is he had 2 pith balls that were actually coated with something that would allow them to hit a bell. And then they had a bell suspended over there, not touching them. Through the center of the bell, it was a conducting wire that went to a large rod that went straight up into the air a long way. He had this in his house, by the way. So what happens is this. When things get favorable to lightning, large amounts of charge are perturbed. You get charge on the surface of the earth and a corresponding charge, negative charge, above it. Well, what happens when you get charge in an area with pith balls is they repel. So the charge was conducted down to them, they repel. And when all of a sudden they get to a certain point, they're going to hit the outer part of the bell, make it ring, and then collapse back on each other. And then charge up and hit. And so with Franklin bells, you can look this up on the internet, you could actually, by the rate of the banging, bam, 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 he could tell how close the storm was. And it's a very interesting way this guy came up with it. The other thing he's credited with, does anybody know the other thing? Has to do with lightning, not the declaration. He also did one thing, supposedly, where he put a key in a jar and flew a kite. That's a fallacy. He didn't do that. But he did some other things with lightning. It's kind of interesting. Franklin was an interesting fellow because he came up with a device that could predict when the conditions were favorable to lightning. His house probably burned down, but I don't know that for sure. But it's an odd thing. I don't think I'd put that in my house. Now, talked about ground loops, talked about that. Next thing I'm going to do, now we're basically, we talked about ferrite chokes, talked about common mode. Now we're into chapter 10, and I'm going to tell you something about chapter 10. We're going to be using the Smith chart. We're going to bring it back up, but we're not going to use it in the standard way. This is a little different. So I want to show you something about this. He goes in and this is microwave engineering. Let me tell you one thing. With microwave engineering, almost always what you're talking about, and I'll bring a piece of this down here next time, is things that are called laminated boards. Now what they are is this. It's a very thin piece of dielectric. On the top it has copper, and on the bottom it has copper. The reason it does is this. You can go ahead and etch away the copper you don't want and give certain widths to things, exact widths, and you can mount devices on them very easily. Now you can do this with something called FR4 board. It's the green board. Has anybody seen FR4 where they mount all that stuff? That's called a lossy laminate. There's also things called Duroid board that have very low loss, very high quality. They're about $100 a square foot. And Duroid board is important when you're building RF components, and here's why. With a board, what they'll usually do, and this is the side of the board, then I'll get to how these Smith charts work. So here, we're going to have certain thicknesses of the copper here. That's just T copper, and that's going to be T copper right here. And then here is the laminate. The laminate is just the dielectric. It has a thickness H, and this has some epsilon relative there in the dielectric. Remember, that's copper right here, Cu. And these are exaggerated. These are usually much, much thinner than the actual thickness, significantly thinner. Well, what we do is this. If I wanted to create something that had a constant impedance, all right, in other words, a transmission line, what I do is etch off all the copper, but except for a certain place. Let me just show you a standard type of transmission line. If this is going to be copper here, then this is the board, and then you just leave all the copper on the bottom. Now, that's going to be a long conductor, right? And you basically have one conductor separated by a certain amount of distance right here, H, where this is a dielectric, epsilon relative. Then you have a second conductor. Well, if you have two conductors separated by a constant distance, you have a transmission line. Now, the dielectric, all right, most of the energy, most of the power, most of the signal, the electric field and magnetic field, is limited in this region. That's the reason these boards are so good. All right, so it's all limited in there. It's not radiating around. It's going to be fairly limited. And now you've got a transmission line where I just put a signal from here to ground, and I've got a transmission line taking it down. I can go and I can route that to different devices. I can take that, and you people are fairly imaginative. If you're looking right on the top of the board, you could take the line and take it out here to an antenna. You could also take the line. This would be done with the standard ways of doing transmission line theory. It has to be impedance matched and things like that. You got to worry about all that. Take it off. You could put some of the signal to something that we'll get to called a splitter that will split the signal off in a couple of directions. You can do a whole lot of stuff with that. And that's what we're going to do with microwave engineering. But we're going to use primarily, we're not building waveguides here. All right. What we're primarily doing is using transmission line theory to actually build devices for very high frequency circuitry. All right, so if you're into gigahertz range circuitry, you need this. You can't do that with short electrical connections usually. So they have, especially if you're at 60 gigahertz, we build these things on boards where everything's connected by a transmission line that's impedance matched, okay? So now, with that said, one of the first questions you probably have is, well, how can I tell what the impedance is? And I'm glad you asked it. In his book, he gives you an exact, well, not exact, an approximation that's pretty good. He shows you this on page 543, and then on 545, he goes through an equation that gives you the impedance of a transmission line for given thicknesses, given widths of the line, and heights or thicknesses of the board. And this is equation 545. I'm not going to write that down. It's all his dimensions that he's talking about is regarding the dimensions he shows on 543. And it's basically what I just told you. So that's an equation for the actual characteristic impedance of any line of any width and any thickness. Do you all see that, class? Now, something I'm just going to throw this out there. I'm not going to spend a lot of time on this. I don't really test you on that equation. I'm just telling you that right now. And I don't test you on a lot of things that have to do with the specific capacitance, inductance per meter, and characteristic impedance of that line. That's not what I really worry about. Those things are done deals right now. They've got all sorts of calculators for that. It's very easy. Nobody does it anymore. What you have to be aware of is one thing. This thing will look like a transmission line up to a certain point. And then all of a sudden it doesn't. Then you get what are higher order modes, and it starts acting like a waveguide. You got to understand this. There's a limit to how high you can drive any transmission line before all of a sudden it breaks down and acts like a waveguide. Even your charter, right? The standard cable that has a center conductor and it has that outer braided shield. It's not charter, it's Spectrum nowadays. But if you have cable providers, if you get a frequency such that a half wavelength in the dielectric exists between the core and the actual outer sheath, then it's going to start acting like a waveguide. You have to understand that. Then signals will start bouncing down instead of, and you haven't had the circular guide yet, but they'll start bouncing around and not coming down where it's TEM. Remember, TEM means the electric field and magnetic field are perpendicular to one another and perpendicular to the direction of propagation. That's what you want for transmission lines, right? E and H are perpendicular to the direction of propagation. There's no bouncing of the signal. I mean, the signal doesn't go bang, bang, bang. But if you go beyond a certain frequency, it does. And that's the limit. And the limiting frequency for these, Wentworth gives an approximation, and he has it on, this is equation 10.7. Let me put it here. Equation 10.7 says Fmax, this is important to know, especially if you're in industry. If you're small companies, it's equal to C divided by 4H, and he's got times the square root of epsilon relative. Do you have to know that? It will be something if I think I'm going to test you on it, I will tell you. It's good to know in general. Here's what it means. If this is the height of the dielectric, and this is the dielectric constant, if you have C as the speed of light over 4H, really C over the square root of epsilon relative is the speed of light in the material. All right? So C over the square root of epsilon relative, speed of light in the material, divide that by 4H, and that's the upper frequency limit. You can't, beyond that, it breaks down. It will not act as a true transmission line. It starts acting like a waveguide, and you get enormous amounts of loss. And that's important when you're designing high-frequency circuitry. I'm just telling you this right now. It means what you really want to go for. If this is upper max frequency, you want it H as thin as possible. Do you all see that? That'll put your upper max frequency way up there. You would like this as thin as possible. Downside of it, of being thin, is the impedance goes way down. Characteristic impedance goes down. So there's the trade-offs that engineers always deal with. I'll spend more time on this next time, and we're going to go into chapter 10 next time. And what I'm going to do is this, hear me now. I'm going to go ahead and hand out some Smith charts. I'll post them. They're going to be called rotated Smith charts. And I'm going to go through these things carefully with you. I'll also take you through a little more of the transmission line, or the actual, sorry, the Doroid board, and hopefully bring down a piece of Doroid board. All right? See you next time. The quiz is going to be on, well, we did the EMC and oh, I got to give you a quiz back too. It'll be on like the actual common mode choke or the homework before that, which is that's EMC. I mean, it was basically analysis of the frequency domain. But we had one quiz on that already, right? The Monday quiz.
We did the DB.
dB microvolts. It was a signal. So you had the 20 dB and 40 dB roll off. Probably going to be on common mode chokes.